Student arranges a toy car track with a vertical loop of radius 20 centimeters as shown. A toy car of mass 150 grams is released from rest at a height of 1 meter at point X. The car rolls down the track and travels inside the loop. Assume G is 9.8 and ignore friction. Calculate the speed of the car as it reaches the bottom of the loop, point Y. Okay, so the first part of this question is a little bit unfair given the context of this chapter. We don't actually look at energy in any great detail until chapter 7, but this is an energy question. Okay, and that comes back to our mechanical energy. And it comes back to the rule we were speaking about before. Whatever you lose in gravitational, you gain in kinetic. So one way we can write that is our change in gravitational is going to be equal to our change in kinetic energy. Okay, so as our car goes down the loop, it's going to lose gravitational energy, but it will gain kinetic. It'll get faster as it goes further down. All right, so our change in gravitational is equal to our change in kinetic. So let's put in our formulas. Gravitational is equal to change in mgh, which is going to be equal to our change in kinetic, 1/2 m delta v squared. Now, one nice thing that you may notice here, and examiners love doing this, they'll give you a problem like this, but they won't give you the mass of the car. And the reason you can do a problem without knowing the mass is your two masses cancel out in this equation. So we don't need to worry about mass. Yeah, we did in this case, but examiners sometimes won't give it to you. So we don't need to worry about our mass here. Okay, cancels out. All right, so if we rearrange this, we are looking for the speed of the car. So we've started from 0. So whatever our change in velocity is, that's going to be our final velocity. So let's solve for v. And we rearrange this, we will get v is equal to 2g delta h square root. All right, so I've just rearranged that above equation, and we get this. We can put change in velocity as well. That's fine. All right, which is equal to the square root of 2 times g is 9.8 times our change in height. Now remember, height always has to be in meters. So we've gone 1 meter change in height. Okay, so the square root of 19.6. 4.43. 4.43, thank you very much. 4.43 units. Meters a second. We're looking for speed. Good. Okay, so our car, now this isn't a circular motion problem yet, but our car at point Y will be traveling at 4.43 meters per second. Okay, just because of whatever we lose in gravitational energy, we gain in kinetic. Calculate the normal reaction force from the track at point Y. Okay, so this is where we need to start thinking about our circular motion. So at point Y, we are at the bottom of the track. Okay, we can consider it circular motion. Okay, even though point Y is just entering the circle, it's still within the circle, so we can consider it circular motion. So we're at the bottom of the track. In which direction is our net force? Up. Good. At the bottom of the track, our net force is up. So F net is up. What about gravity? Down. Fg, what about normal? Up. So Fn. Okay, so upwards is going to be positive, downwards will be negative. And so if we put our net force equation in, equals Fn plus Fg. Okay, all of our forces added together. So if we rearrange this, we are looking for our normal force. So Fn will be equal to F net minus Fg. All right, so let's put in the data that we know. So F net is given by mv squared on r, and Fg is just mg. All right, so what was the mass? 0.15. So I'm going to run out of room here. Why did I do that diagram right in the middle? 0.15 times 4.43 squared. Okay, that was our speed on the radius of the circle. Again, needs to be in meters. So 0.2. Okay, that's going to give us our net force. Let's calculate that because I've run out of room. 0.15 times 4.43 squared. 2. So we get 14.7 as our net force. Our mg is equal to 0.15 times 9.8. 1.7. Sorry, 1.5. Now, where we need to be a little bit careful here is our gravity is downwards, okay, compared to our net and our normal, which are upwards. So when we do F net minus Fg, we're doing F net minus our negative Fg value. All right, so we have our normal force is going to be equal to 14.7 minus negative 1.5. So our normal force will be 15. Oh no, that's not right. 16.2. 16.2 newtons. Okay, so it's really important that you have these directions around the right way. Okay, so 16.2 newtons. Now, if we work it out, our normal mg is only 1.5 newtons. So our normal weight force for this cart is 1.5. Our normal force is 16.2. So the apparent weight will be much heavier. So if you happen to be a really tiny person inside this really tiny car, you would feel much heavier than you would normally. Okay. Next, what is the speed of the car as it reaches point Z? Okay. Again, this is an energy question. All right. Remember, whatever it loses in kinetic, it gains in gravitational and vice versa. So there's actually a couple of ways you can do this. You can take its kinetic at point Y and work out how much of that kinetic it's going to lose to get back up to point Z and, change your velocities there. You can also do it from the start. You can take your starting point as X, where you have 0 kinetic energy and all gravitational, and if you move it down to Z, so if you lose that much gravitational, you can work out your kinetic that way. Oh, I've done that too high. Okay, so it doesn't matter that it's gone down and back up. If there's no friction, we can still just consider it as going down to get that speed at that point. Okay, in fact, let's do that. So again, our change in gravity or gravitational potential energy is going to be our change in kinetic energy. So our change in mgh will be equal to 1/2 m change in velocity squared. Our m's cancel out. And so from that equation on the previous page, our change in velocity is going to be equal to 2gh, I should put delta h there, 2g delta h square root. Okay, so it starts at point X, it finishes at point Z. Its change in height from point X to point Z is what? 0.8. 0.8?
0.6.
0.6. I see what we've done. There's two 20 centimeters. 20 is, yeah, 20 is the radius. So our change in height is 0.6. 0.6 meters. All right, so let's pop our values in. Now, by the way, before we calculate this, let's apply a little bit of common sense and think about the answer we're expecting. Our velocity at point Y was 4.43. We would expect our velocity at point Z to be less than that because it's lost speed going up. But we'd certainly expect it to be more than 0 because it would have gained energy from there or gained kinetic. So let's assume we're going to get less than 4.43 and see if we're right. So square root of 2 times 9.8 times change in height 0.6. Yep, I get, yeah, call it 3.43. Does that pass our common sense rule? Yep, does to me. So it's slower than it was at point Y, but it's obviously faster than it was at point X. Okay, so now we know the speed of the car as it reaches point Z. All right, now buckle up. There's a trick question coming. What is the normal force acting on the car at point Z? Okay, so here I'm going to show you something that is going to look weird, but it's true. So what does a car look like at point Z? It's upside down. All right. So, oh, you've twigged. Yep, you're absolutely right. So there is our car, upside down. Which direction is our net force? Down. Center of the circle. It's moving in circular motion. Our net force must be down. Which direction is gravity? Down. Gravity's always down. That's easy. FG. Which direction is the normal? Down. All right. The tracks pushing against the tires, downwards. So here we have this situation where all of our forces are acting in the same direction. Now, how can that possibly be with our cart still not falling? Well, remember, this is circular motion. These forces are changing its direction. So at this point, it is still traveling horizontally with a velocity. These forces are just getting it to change direction as it comes around. So this is perfectly valid. All right, so now, again, F net is equal to Fn plus Fg. Now here they are all in the same direction, so we don't need to worry about negatives. Isn't that nice? So we want our normal force. Rearrange. Fn is equal to F net minus Fg. All right, so now our F net, hopefully I've given myself enough room here. F net is mv squared on r minus mg, so 0.15 times 3 point, what was it? 43? 3.43 squared on our radius of our circle is still 0.2 minus 0.15 times 9.8. 5 squared over 0.2. And I get a normal force of 7.35. So Fn is equal to 7.35 newtons.
Do you get directions?
Sorry? Yeah, direction's not bad. So, downwards. Okay, now you might notice this normal force is larger than it would normally be traveling horizontally. But you think, well, that's weird because at the top of a hill, shouldn't you be lighter? The thing is, we're not at the top of the hill. If we inverse this picture, we're at the bottom of an upside down dip. So you would feel heavier. You'd be pushed further into the seat at the top of that hill. Okay? All right, so that is an example of a vertical circular motion problem. The same thing applies. Just every time you do one of these, draw a diagram and make sure you know which direction those forces are acting in. Then that'll help you with your negatives and your positives. As I said, with these particular examples, A and C are energy questions, so you'll need to use changes in energy to work out speeds. But parts B and D, you will need to work out the direction of these three forces to work out what's going on in the problem. All right, have a go at the next one. If you're stuck, please let me know.